What I have here is a block of 3 D-cell batteries in series. So we have a total voltage of about 4.5 volts. It's wired in series to a light bulb, which is wired in series to what's called a supercapacitor, which is just a capacitor with a ridiculously large capacitance. In this case, 0.47 farads. What I'm going to do is I'm going to complete the circuit, and I want you to predict what's going to happen to the brightness of the bulb. So go ahead and pause the video, make your prediction, and then we'll resume. Okay, here we go. Okay, so now what I'm going to do is I'm going to take the batteries out, and I'm just going to connect the capacitor and the light bulb in series. So there will be a period where the circuit will be completely disconnected, and then I'm going to reconnect it so that just the capacitor and light bulb are in series. Again, pause the video and make your prediction about what will happen. Okay, so here we go. All right, well, is that what you predicted? Let's go ahead and take a look at what's going on here. All right, well, let's start first by thinking actually about the second demo that you saw. So the first demo, I was charging the capacitor, and when I disconnected it, the charges didn't have anywhere to go, and so the capacitor remained charged. And this is actually an important safety issue when handling capacitors. Whenever you go and put capacitors away, you always need to make sure that they have been properly and safely discharged, because otherwise they'll sit there and hold their charge for very long time. And if you just grab a capacitor and you manage to get both leads to touch you, you can get quite a shock. So here, so we'll start by looking, so then we go ahead and connect our capacitor. And so I'm going to imagine, instead of us having a light bulb, I'm going to imagine that we have a switch and that it's going through a resistor. And the only reason I'm choosing a resistor is that a light bulb is decidedly non-ohmic, and I want to think about ohmic devices here. So there's my resistor, there's my capacitor. Now the capacitor is going to hold some initial charge, Q0. And let's just say, for purposes of discussion, it's the upper plate that's positively charged and the lower plate that's negatively charged. So all right, we go ahead and close our switch. Now when we close our switch, the capacitor now has a way to discharge because the fringe field will go ahead and reset an electric field through the wires to pull charge off. And when we've thrown the switch, we will have a current that is flowing clockwise here. So remember here, the electrons are going to be getting pushed off the plate by the fringe field here, attracted onto the plate by the fringe field here. So the electrons are going around counterclockwise, but since the electrons are negative charge carriers, the conventional current points in the opposite direction, so the conventional current flows clockwise. Now here, there are no charges flowing between the plates. There is no way for the chart in normal operation anyway, for a capacitor to have current flow this way. If you do, you're jumping a spark, and the next thing that will happen is you'll see a nice little column of blue smoke coming out of your circuit, and that's usually a bad thing. All right, so we can go ahead and start analyzing this circuit by using Kirchhoff's loop law. So I can just go ahead and start in the lower left-hand corner and walk my imaginary dog around clockwise. So as I walk along here, I go through the capacitor. The voltage increased because here's the negative plate, here's the positive plate. This is the higher potential side of the capacitor. And it increased by Q over C, where Q is whatever the charge is on it at the moment. Because remember, once charges start coming off of this to go the current, the charge will deplete. So this is not the same deal as a battery. Here we really are storing charge, and as the charge comes off, it depletes. A battery never stores charge. It just acts as a conveyor belt to shove charge along. A very different thing. Okay, so as I continue along walking my imaginary dog, I go through the resistor along the direction of the assigned conventional current. So that's minus IR, and that will equal 0. Now let's start by trying to figure out what the charge is on the plate as a function of time. So we can do that by observing that at all times the current through here has to be equal to the rate of discharge of the capacitor. So the rate of charge, if it were being charged, that would be dq dt. So discharge is minus dq dt. So we observe that the current has to be minus I dq dt. And here, because it's discharging, the current is starting from some higher, the charge is starting from some higher value, going to a lower value. So that's going to be a negative derivative here. So minus sign indeed gives us the positive current that we need. So if we go ahead and substitute that into our loop law expression, we get Q over C plus R times dq dt equals 0. All right, and this is an example of a beast called a differential equation, and for the level that I'm presenting here, I don't expect you to be able to solve these signs, but I want to show you how it's done so you have some flavor for how we can think about this. So it turns out that with these kind of equations, you always solve them by guess and check. And the first thing I'm going to do is I'm just going to divide both sides through by R, and I'm going to rearrange a little bit. And this is just to help let me think about this maybe a little more clearly. So this is going to be dq dt plus 1 over R times C times Q equals 0. Now, what I'm trying to do is I'm trying to solve for Q as a function of time. And like I say, this sort of a thing can only be done by guess and check, but let's start to think about what a good guess might look like. When I look at this, I see that I have the thine and I have the derivative of the thine, and somehow I need the two to cancel. So this means that whatever the functional form of this is, I have to have the same functional form over here. And so I think back and think, what kind of functions look more or less like themselves if I differentiate them? And I think, oh, hey, exponentials. So this will help us to build up our guess. We're going to guess something of the form Q is equal to, well, I'm going to need a Q naught because at time 0, I need the charge to be equal to the initial charge. And then I'm going to guess something of the form e to the minus t over tau. And the minus sign here is because when I differentiate this, that will make this a negative so that I at least have some hope of canceling. We will have to solve for what tau will need to be to make the cancellation happen if this is a good guess, and it is. So this quantity tau gets the name the time constant. And if we think about its units, we realize the units have to be seconds. And the reason we realize this is that with this e to the minus t over tau business, whenever I stick something in exponential, it has to not have units. If, say, tau didn't have units, I would be left with e to the minus some number, but then I'll have e to the second sitting out somewhere. And I don't know what e to the seconds means. So I need to have the seconds cancel out. So from that alone, we know as an additional sanity check that when we solve for our time constant, it better have units of seconds. Okay, so that's my guess. And now I'm going to go ahead and do the check. So to do the check, what we do is we just simply stick my Q in here and here and see if it works out. So here I need to differentiate this with respect to time. Okay, so I differentiate that. Q naught's a constant. Great. And then differentiating this is going to give me minus 1 over tau e to the minus t over tau. And then here, for the second term, all I need to do is just substitute in. So plus 1 over RC Q naught e to the minus t over tau. And that needs to equal 0. So to get these to cancel out, we see that all we need to have happen is that tau equal RC. So we will demand that tau be equal to RC. And I will leave the sanity check of verifying the units to you, but yes, believe it or not, ohms times farads is indeed seconds. So the units do indeed work out. All right, so with that, let's start to take a look at what's happening with our charge and our current as functions of time. So we got that our charge was Q naught e to the minus t over tau. Let's make that look a little better. Minus t over tau, where tau is equal to RC. And if I differentiate this, and there will be minus signs that cancel out, so I'll be okay. You can also come up with a similar expression for the current. That'll be the initial current in the circuit times e to the minus t over tau as well. So let's go ahead and graph that and see how we can interpret this. So I'm plotting the charge on the capacitor as a function of time. Let's say that this is Q naught. And I'm going to mark off 1 and 2 time constants just to help think about things a bit. So this is going to be a decaying exponential. So the charge on the capacitor will asymptotically approach 0. However, after a few time constants, the charge will be quite low. So now if we look at one time constant, a nice magic number to remember here is that we will be down to 1 over e times the initial charge, which works out to be 37%. So we will be at 37% of our initial charge here. And then at this point here, at 2 time constants, that would be 37% of 37% of our initial charge. And at 3 time constants would be 37% of 37% of 37%, and so forth. So if you just keep the number 37% tucked in the back of your mind, it's really useful for being able to estimate these things. Now the voltage across the capacitor will go directly as the charge. So the voltage across the capacitor is also dropping like this. And by Ohm's law, twinkle, twinkle, little star, delta V equals I times R, as the capacitor voltage drops, the current through the resistor also has to be dropping at that rate. So this gives us some clue for how this is going to work. Since the current will have the exact same shape graph as the charge, then at any given time, the rate of charge coming off the plate is directly proportional to the plate, to the charge on the plate itself. And whenever you see something like that, you should immediately be thinking exponentials. If the rate of decay of something is proportional to however much of it you have, there you go. Same kind of thing happens, for instance, with radioactive decay. The number of nuclei, the rate at which nuclei decay, depends on how many nuclei you have. The more nuclei you have, the more of them are apt to decay, right? And so it turns out that radioactive decay follows this exact same sort of pattern. It's the sort of thing that shows up all over the place in nature. So it's a worthwhile thing to have tucked away in your mind. So now let's go ahead and turn our attention to the charging situation. So we were looking at discharging before. Now let's go ahead and look at charging. And once again, I'll replace our light bulb, which was serving as a low-tech ammeter, with a resistor so that we can make our devices ohmic. So again, I'll have a battery here. I'll have a switch here. We'll put in a resistor and a capacitor. So here's the battery EMF. There's the capacitance. Okay. So again, let's try to intuit here what are functional forms for the current in the circuit, the current through the circuit, and the voltage across the capacitor are going to look like. And we'll use that to help guide our guesses for doing the guessing and checking. So if I think about the current as a function of time, well, if I go ahead and close the switch, like so, we know that we will have a current going through the circuit, including through the battery, because now we have a battery that is actually doing work. Oh, we did not want it to turn into a pretty rectangle like that. There we go. So our current I is flowing clockwise through the circuit now. So if our capacitor was initially discharged, which means that Q naught is equal to 0, as we're going along, first let's think about what the voltage across the capacitor is. It's initially 0. So that means that the voltage across the resistor is equal to the voltage across the battery. So we will be pulling maximum current initially. Whatever that current is, let's call it I naught. Now, as we charge, now keep in mind technically, even though I drew an arrow through here, technically there are no charges moving between the plates. People get a little lazy about it and they'll draw an arrow, but remember, there's no actual charges going between the plates here. So what's now going to start happening is we're going to be building up a positive charge here and a negative charge here as the battery takes electrons off of this plate and moves them to that plate, giving us an electron current that's counterclockwise. So we have a conventional current that's clockwise. So we're starting to pick up a charge plus Q here, minus Q there. So we say that the charge held by the capacitor is Q. Well, as this charge builds up, what's happening to the voltage across the capacitor? Yeah, it's going up. So if the voltage across the capacitor is going up, then by Kirchhoff's loop law here, the voltage across the resistor is going down, which means that the current is going down. And so we know that that means that the rate at which you're putting charge onto the plates is decreasing. So we expect the whole thing to slow down. So we're expecting that the rate at which the current is changing to end up being proportional to the current itself. So we're expecting some sort of exponential decay like we saw before. Now for the charge or the voltage on the capacitor, either one, because they're directly proportional. So we'll say Q and then we'll say delta VC. Since they're directly proportional, we know initially the charge held is 0. And we know that if we think about the voltage, so let's actually just focus on the battery voltage for the moment. If we think about the voltage, we know that it has a maximum value. When we are fully charged, we can't move any more current through, and the capacitor will be acting like a break in the circuit. At that point, the current is 0, meaning the voltage drop across the resistor will be 0 by Ohm's law. So that means the voltage drop across the capacitor will be equal to the battery EMF. So we've worked out that our maximum voltage across the capacitor will be the battery EMF. We know we start from 0, and we know that the rate at which we're putting on charges is decreasing with time. So we know that initially the voltage should be going up quickly, and then it should asymptotically approach the battery EMF. So we might not know exactly what that looks like just yet, but at least when we are looking at our solutions, we should be trying to get something. Now, we can actually do this one, believe it or not, by directly integrating it. So at least to get the charge held on the capacitor. So let's just do that as an example. So we'll go ahead and again, we'll write Kirchhoff's loop law here. So when I write Kirchhoff's loop law and I'm walking my imaginary dog along, I'll start in the lower left-hand corner and go clockwise. So here I'd leave the battery at the positive terminal, so I'd say that that's plus the battery EMF. I'm going with the assigned current, so that's minus IR. And then here, I am going, I'd leave the capacitor at the negative terminal, so the voltage decreased by a total of Q over C, and that equals 0. All right, now here we can make the observation that the current is just plain dq dt without a minus sign this time. And this is because we are putting charges onto the capacitor, not taking them off. So the rate at which charges are passing through the resistor is the rate we're packing them on here. So here I is dq dt. So we can rewrite this to say it's E minus R dq dt minus Q over C equals 0. And that still looks a little ugly. Let me, not that it'll seemingly help too much at the moment, but let me go ahead and just divide everything through by R like I did before. I'll have E over R minus dq dt minus 1 over RC times Q equals 0. So this gives us some hope that we'll have a time constant with an RC in it, and you'd be right. All right, so let's rearrange this best we can. So the goal here is we'll do this by trying to directly integrate things. So I'm going to say dq dt here is equal to 1 over RC Q minus E over R. So if I times top and bottom here by C, I can put things on a common denominator and get that this is, whoops. Yep, nope, I'm right. This is Q minus C E over RC. And so the trick that you can do here to take this further is you can make a substitution. And physicists are a little annoying here. We're not going to call it U. We'll call it Q prime minus C E. And yes, I know mathematicians, when they use a prime, they mean to take the derivative. Physicists actually put a little dot over the letter. So when a physicist uses a prime, it means the thing that's like the thing, but is not exactly the thing. So I'm calling this Q prime in the traditions of physics. But the big deal here is if I differentiate this, dq prime dt is just dq dt, because this is a constant, so that drops out. So this allows me here, I can replace this dq dt that I had right here. I can just replace that directly with q prime, and then this is q prime, and I'm all good. So I am left with dq prime dt is equal to minus 1 over RC q prime. And we've solved this one before. We know the answer, but this time let's just do it by integrating it just to see that it can be done. So if I cross multiply, I will get dq prime over q is equal to minus 1 over RC dt. And yes, I know mathematically, legally, I'm not cross-multiplying, but just accept it. So I will integrate this from our initial charge Q naught prime to our final charge Q prime. And yes, I know I made the limit of integration the same as this. We do that all the time. Deal with it. As long as I integrate this from time 0 to time t. All right. Well, this is going to be the natural log of Q prime evaluated from Q naught prime to Q prime. This is just going to be minus t over RC. So that's looking good. So evaluating this is going to be the natural log of Q prime minus the natural log of Q naught prime. It's minus t over RC. If I want to be more clever, I can say this is the natural log of Q prime over Q naught prime. It's minus t over RC, and then I can exponentiate both sides, or take the anti-log of both sides, and I get Q prime over Q naught prime is equal to e to the minus t over RC. And yes, we are going to interpret our RC as our time constant tau again. So we can get this into a final form. Q prime is equal to Q naught prime times e to the minus t over RC. Now we just have to go back and put in what these were. So this will be Q minus CE, and this is going to be Q naught minus CE times e to the minus t over RC. Now Q naught is equal to 0. So I can go ahead and do that because the capacitor is initially discharged. So if I add CE to both sides, I get Q is equal to Q is equal to CE minus CE e to the minus t over RC, or finally Q is equal to CE times 1 minus e to the minus t over RC. So our initial guess was right about the functional form. It is something that asymptotically approaches a limit here. So to get the capacitance, so to get the voltage, we can just divide both sides through by C. So dividing both sides through by C, Q over C is the battery voltage at all times. That would be equal to the EMF times 1 minus e to the minus t over RC. And so we can see we start, when I put in t equals 0, e to the 0 is 0, 1 minus 1 is 0. We start with a voltage of 0. We, at infinity, this will be e to the negative infinity, so then this would be 0. So our asymptotic bound is indeed e, and we expect it to ramp up quickly and then slowly approach our asymptotic bound. So this is indeed what we have. So since 37% is our magic number, at one time constant, now this is going to be 1 minus 37%, which is 63% of the battery EMF. Now to get the current, we can go ahead and take what we had before. I can go ahead and differentiate this with respect to time. differentiating that with respect to time, that's going to give me nothing. Differentiating this is going to be a negative 1 over RC, and I have a negative already, and the C's will cancel, so I'll be left with E over R, the EMF over R, times e to the minus t over RC or over tau, whichever you prefer. And again, this here is going to be my initial current. I shouldn't make it look like I'm canceling it out. This is my initial current here, because remember, when the capacitor is completely discharged, it momentarily acted like a wire. In fact, that's a good way to remember these things. A completely discharged capacitor will momentarily act like a wire. A fully charged capacitor will act like a break in a circuit. So when the capacitor is momentarily acting like a wire when it's fully discharged, we had maximum current as if the capacitor weren't even there, and that's what you would have. All right, so that's an awful lot, and you might be wondering what sort of practical applications you might have for this. Well, one thing, when you go and set up these kind of situations, you can say with the charging capacitor, because we saw that the current is decaying with time. If you need to build in some sort of a circuit, some sort of a branch to a circuit that just operates for the first little bit and then basically goes away, you can go and stick in one of these RC combinations into that branch, just to energize the warming up circuitry or whatever it is that you need. More practically, though, is these sort of things often get used for timing. There is a chip called a 555 chip, and it's got a cousin called the 556, which has two 555s on the same die. And what they do is they take advantage of this exponential charge and decay rate. What the 555 will do is it'll charge up the capacitor, and it does it in a way where it shorts out the resistor so that it can charge the capacitor up very quickly, and then it lets it discharge through the resistor. And the values of the capacitance and the resistance are set by the electronic designer. It measures the voltage across the capacitor, and when it drops down to a certain level, it sends out a pulse to indicate that a set amount of time has elapsed, and then promptly recharges the capacitor to do it again. So this sort of circuitry is actually like the basis of like those really cheap egg timers that you can get at any at any cooking supply store or any home goods store, that kind of thing. So let's just imagine then that we have a 10 microfarad capacitor. Nice typical value for these kind of timing circuits. And we're just going to let it discharge through a 1 kilo ohm resistor. Again, a nice typical value. Let's say that the initial charge held on this was 20 microcoulombs. What we want to know is how long until our charge equals 10 microcoulombs. Well, okay, we've worked out that this is going to be a discharging capacitor situation here. So we would go ahead and use the relationship that Q is equal to Q naught times e to the minus t over RC, or t over tau, whichever you prefer. So we need to solve this for t. So let's go ahead, times, not minus, e to the minus t over RC. Sorry about that. And of course, I caught that because the units didn't check. When I had the minus sign there, this had units of coulombs. the exponential can only ever be a number, so I realized that I couldn't subtract those two things. All right, so let's go ahead. We need to get t by itself, so first thing we can do is divide both sides by q naught. So e to the minus t over rc is equal to q over q naught. The next step will be to take the natural log of both sides. So the natural log of e to the minus t over rc is just plain minus t over rc. And over here we have the natural log of q over q naught. So we can finally solve for the time as being, minus rc times the natural log of q over q naught. And you might be worried about that because you're seeing this minus sign sitting in front, and that would seem to be implying that we discharged before we were charged or something. But that's not the case, because remember, q is going to be less than q naught. So that means that this fraction is going to be less than 1. And the natural log of a negative number, of a number less than 1 is negative. So this natural log will be negative, canceling that negative, giving me a positive number. So we will have negative 10 times 10 to the negative 6 farads, because it's 10 microfarads. And we said it was a 1 kilo ohm resistor, so 1,000 ohms. This will be times the natural log of, we said initially it was 20 microcoulombs and discharged to 10 microcoulombs. Now here I don't need to convert the micros, because as long as this is microcoulombs and that's microcoulombs, that's compatible units and the units cancel. And so sure enough, this is actually the natural log of a half. And the natural log of a half is indeed a negative number. And so when we go ahead and crunch this through, we will get 0.00693 seconds. So this will be 6.93 milliseconds, which is actually a very typical kind of period that we might have in such a timing circuit. Alrighty, in the next video we will go ahead and take a look at how to use Kirchhoff's rules when we don't have any other way to analyze the circuit. So catch you over there.